name's Musulin, who's at home doing a COVID test and waiting for the result. It's my pleasure to be the chair. You might have noticed that the two CUAVA sessions, or CUAVA 2 payload sessions, have been combined into one. And that's partly because Anita Ho-Bailey talked yesterday and is unable to be here today. She's got other deadlines she has to meet. And then I will be presenting for Joe Kashan, unfortunately, or fortunately as the case might be, as the last talk. So we'll start off with Quinn Musulin, then we'll go to Joshua Critchley-Marrows, Chris Betters, etc., etc. I just can't remember 7 names in a row. So CUAVA 2, you heard yesterday from Shirley-Ann Bai a little bit about the CUAVA 2 mission. We're not going to do a recap of any significance here, except to say that it's a 6U CubeSat. It's meant to go to 550 kilometers sun-synchronous orbit, and it's the second CubeSat for the ARC Training Center for CubeSats, UAVs, and their applications, otherwise known as CUAVA. It will have almost the same bus as the Waratah Seed rideshare satellite, which also won't do any other spooking for. And I think that's probably the summary you need to have at the moment, and we'll focus on the payloads in this session. And the first such presentation is by Quinn Musulin, and he'll be talking, as you see here, about the EDI instrument, which some others would call the plasma wave receiver. So, Quinn, let's go ahead.
Thank you.
Ada, do you want to go? You've got it. Yeah, okay.
Okay, thanks, Steve. So I'm here to talk to you today about the electron density debris instrument, which is a CUAVA 2 payload. This is a collaborative effort between myself, Ibra Snitz, Joe Kashan, Phil Leong, and Peter Axtons. And the purpose of the instrument is to detect ionospheric plasma density and temperature on board of a CubeSat, as well as detect particle impacts on the CubeSat as well. So, first of all, why do we care? The ionosphere and ionospheric models are kind of poor. We do have ways of sounding the ionospheric parameters, such as ionosongs. Some of you may know about these, but they're sort of set up over land and not over the poles of the ocean. Sorry, most of the time. So this is a lot of the globe that we're not measuring the ionospheric parameters continuously for. And there are certain technologies which do rely on knowing the plasma parameters are continuously, such as over-the-horizon radar and radio systems. So these rely on real-time ionospheric parameters for efficient refraction of incident radio waves, for example. The DSCG does have JORN over-the-horizon radar network, and they are launching the Buccaneer mission, for example, which shows that there is sort of some interest in calibration techniques for these sorts of technologies. We also have the benefit of being able to potentially detect space weather events if we have a device in situ. So variations in ionospheric plasma temperature and density due to coronal mass ejections, for example, are detectable if you have a sensor in orbit. And also very topically, we have space debris. Current tracking technology allows for a minimum of about 5 centimeters diameter debris size from tracking from ground. So how is it done? So what we want to do is measure the electric field power spectrum between 0.1 and 20 megahertz on board of a CubeSat. And so if we do that, we can get a whole lot of interesting science from our power spectrums. So we can detect thermal plasma waves or quasi-thermal noise. So if you have an antenna in a plasma, the natural fluctuations and frequencies of plasma waves are detectable and measurable. And so the positions of those give you your plasma density and temperature. And then if you have, say, a particle impact on your CubeSat body, the resultant plasma cloud is then also detectable as a voltage signal. So this is a theoretical model of what we're looking for. So on the left side, we have the contribution to the spectrum due to debris impacts and shot noise. And the peaks here are our quasi-thermal noise. And so once again, the positions of these peaks and frequency will give us our density and temperature. And the left side is the contribution to dust noise and shock noise. So the idea is that we have our own power spectrums that we then fit these theoretical models to, which then give us all these plasma parameters. I'll just mention quickly that this technology has been used many times in the past. So plasma wave receivers have been used on Ulysses, Stereo Wind, and the Parker probe currently as well. And so for like most CubeSat technologies, the miniaturization of the electronics for CubeSat applications is what's normal. We also have other challenges such as a large frequency range, 0.1 to 20 megahertz, a smaller antenna, and a very small voltage that we're trying to measure on the antenna. So if we're lucky, 40 microvolts. Okay, so this is a system overview. It's just split up into 3 parts. So we have our antenna, which is a dipole antenna. I've got a PCB here, and mounted on the PCB is a microprocessor for digital signal processing. Okay, so I've just got a picture here of it all mounted in a CubeSat. Eddy will exist somewhere in the middle, and then on the tops will be the antenna mounts with measuring tape antenna, which has been used on quite a few missions in the past. So a dipole measuring tape antenna. So the reason why we want to go with measuring tape potentially is that it is easily storable and deployable. And it has been used on other CubeSat missions, so we do know that it works, or should work, such as, once again, the DSTG's Buccaneer mission does use a sort of similar concept for their receiving antennas. Okay, so this is just a key features of the PCB that we have designed. So it is a fully differential variable gain amplifier with 4 stages. We can control the gain from software, and so we have a gain range of about 800 to 8,000 times. And this is overkill. We don't really need this much gain, but we do want a bit of gain variation in case we get into orbit and something is wrong with the models potentially. So we have a bit of an ability to tweak the gain and amp up our signal. We also just have some low-pass filtering to make sure that we remain in the frequency band of interest, and there is some SD card storage as well. Okay, so this is just an overview of the software that is running on the device. So what we do is we first sample with our ADCs. We do 2048 point FFTs. We average these FFTs and do a power spectrum, and this is repeated about 30 times a second. So it happens pretty quickly. And that ensures that we get an accurate picture of ionosphere conditions over that entire second. So it's sort of a chopping of that second up into little chunks. So if we do this quickly, this gives us about 10 kilometers spatial resolution of the ionosphere and a 20 kilohertz spectral resolution of average matter spectra. The power consumption of the PCB and the microprocessor is about 1 or a little bit over a watt, so pretty low. And the data rate that we're looking for to capture is about 8 kilobytes a second, or 30 megabytes an hour. But we're still unsure about how the modes that this is going to run in. So whether or not we do this for a minute or for a number of minutes, still working that out. Okay, and then I just have a few slides about our engineering model testing. So this is a picture of our engineering model. And if you want to determine whether or not your model works to measure electric field, what you do is you test for radio stations. So this is just one of our standard spectra from the device. And on the left-hand side here, we see all of the sort of AM radio stations being detected. So if I sort of focus in on this region, there are some popular or unpopular radio stations here that we're detecting. So ABC Sydney Radio, 2GB, 2UE, sports, etc. Okay, that's my last slide. So conclusions. So hopefully, if we can get these power spectra from the ionosphere, we will be able to improve ground-based technologies. We can help potentially detect space weather events and model debris. Our engineering model does show that we have the ability to measure AM radio stations, and I didn't think I would have time to show plasma chamber tests, but I could have. We have been doing some testing in a plasma chamber as well to verify its ability to detect thermal plasma noise, for example. The flight model we built next week, I'm hoping to get the PCB delivered tomorrow, and then we just have some shape tests and then submission later in the year. Thank you.